From now on, we're going to spend quite a bit of time going through a catalog of integration techniques. So before we start with new integration techniques, we're going to do a quick recap of what you already know and go over a few standard tricks that do not go as far as being really an integration technique per se. So the most basic thing that you've seen in Calc 1 is that to calculate a definite integral, all you need is to find an antiderivative, capital F, and evaluate it between the upper and lower bound of integration. So if you find an antiderivative, then you just need to evaluate this antiderivative at the upper bound and the lower bound and take the difference to get the definite integral, assuming of course that you're integrating a function that is continuous on the interval. So it's all about antiderivatives, and so we use the integral sign for a general antiderivative of the function f, and it's called the indefinite integral. And so you have seen standard formulas to obtain antiderivatives for certain kinds of function, most prominently powers of the variable. So if you have x to the n, where n is any real number different from -1, then an antiderivative is x to the n plus 1 over n plus 1. All of the antiderivatives are up to a constant. The case where n is -1 is something that we've seen in this course, not in Calc 1. And an antiderivative of 1 over x is ln of absolute value of x, up to a constant. You've seen in Calc 1 that integrating is a linear process, in the sense that if you multiply by a function by a constant and integrate that, it's the same as multiplying the constant by the integral of the function, and similarly the integral of the sum is the sum of the integrals. So with these two formulas together with the integral for the power of the variable, you can integrate any polynomial function, for instance, and a lot more. Other standard formulas that you have seen is antiderivatives for cosine, sine, and secant squared. This is just turning around the formulas for differentiating sine, cosine, and tangent. And additional formulas that we have seen in this course are the integral form for the derivative of e to the x, so namely the integral of e to the x is e to the x, integral of a to the x, where a is some positive number different from 1, is a to the x over ln of a, and the integral of 1 over root of 1 minus x squared is given by arc sine of x up to a constant, and the integral of 1 over 1 plus x squared is given by arctangent x up to a constant. So of course all these formulas are formulas that you're supposed to know. The basic technique that you have seen in Calc 1, pretty much the only real tool that you have beyond standard formulas like those that we just have seen, is substitution. So substitution is really just turning around the chain rule and writing the chain rule for antiderivatives. So if you integrate a function that can be seen as f of g of x multiplied by g prime of x, then you can introduce a new variable corresponding to g of x, let's call that u, du is g prime of x dx. So formally you can rewrite that integral as the integral of f of u du. That's for antiderivatives. Of course, for definite integrals, they correspond to antiderivatives via the fundamental theorem of calculus, and so you have a form of substitution for definite integrals. It's exactly the same thing, except that when you use substitution for a definite integral, you also have to change the upper and lower bound of integration. Indeed, when you integrate f of g of x, g prime of x dx from a to b, the lower and upper bound of integration mean that the range of values that x assumes is from a to b. So when you change the variable to u and you have the integral of f of u du, you need to specify the range of values that u assumes. And here, to get these values, you simply plug x equal n, x equal b inside the formula u equals g of x. So when x is a, u is g of a, and when x is b, u is g of b. So g of a and g of b give you the lower and upper bound of integration in the new variable u. So let's take a look at an example. Let's say we want to integrate 4x plus 3 divided by the square root of 2x squared plus 3x minus 1. So we have a composite part here, which is 2x squared plus 3x minus 1 that is plugged inside the function 1 over square root of x. So the natural choice of a new variable is 2x squared plus 3x plus 1, in which case du is the derivative of that function times dx, so it is 4x plus 3 dx. Turns out to be exactly what we have at the numerator. So formally this integral can be rewritten in terms of u as du over square root of u. I can see that as a power of the variable u. It's u to the negative 1/2. So if I use the power rule, I get for an antiderivative u to the negative 1/2 plus 1, that's u to the 1/2, over 1/2. If I divide by 1/2, I'm really multiplying by 2, so I get 2 square root of u up to a constant. Of course, the goal here is to obtain an antiderivative of the function as a function of x. So we replace u by its value in terms of x, and we obtain 2 square root of 2x squared plus 3x minus 1 up to a constant. One formula for integrals of trig functions that I didn't write in the previous slide was the integral of tangent x. With substitution, we can obtain this integral easily because tangent x is really just sine x over cosine x. And then if you take as a new variable cosine x, you see that du is negative sine x dx. In other words, what you have at the numerator is the opposite of du, so that this integral can be rewritten formally in terms of u as negative integral of du over u. An antiderivative of 1 over u is natural log of absolute value of u, and u was cosine x, so we get negative natural log of absolute value of cosine x. One of the properties of the natural log that we have seen is that if you have a multiplicative constant in front, you can bring in inside the log as a power. So we get natural log of absolute value of cosine x to the negative 1. And cosine x to the negative 1 is 1 over cosine x, in other words, secant x. So a standard way to write that is natural log of absolute value of secant x up to a constant. Now, substitution is not always as straightforward as for the examples that we just have seen. Consider, for instance, this integral, where we're trying to find an antiderivative of 1 over x minus root of x. There's not an obvious composite part, and so there's not an obvious choice for a substitution here. However, sometimes there is a trick in rewriting the integral that gives you an idea of what to do. For instance, we could try to factor out the square root of x that we have at the bottom. And if I factor square root of x out of x, I get square root of x. So in other words, another way to write this integral is as integral of 1 over root x multiplied by root x minus 1. Now under this form, and of course it's not that obvious to see that these are the same thing, but if you do see that, then under this form it's more natural to find out what to use as a substitution. Because the derivative of root x minus 1 is the derivative of root x, which is 1 over 2 root x. So that means that the 1 over root x that we have is a constant multiple of the derivative of root x minus 1. That means that u equal root x minus 1 is a natural choice, and du is 1 over 2 root x dx, which I can write dx over root x, which is the part that we really have inside our integral, is 2 du. So I can replace dx over root x by 2 du and root x minus 1 by u, and I obtain 2 integral of du over u. An antiderivative of 1 over u is ln of absolute value of u, and u was root x minus 1, so we obtain 2 natural log of absolute value of root x minus 1 up to a constant. Other standard formula that we can obtain easily from the previous ones using simple substitution, and I'm not going to do every single one of them. I would leave that as exercises for you to check. Is that if you integrate sine of kx, where k is a constant, of course a non-zero constant, then you get negative 1 over k cosine of kx up to a constant. If you integrate cosine of kx, then you get 1 over k sine of kx. If you integrate e to the kx, you obtain 1 over k e to the kx. For each one of these three, of course, the simple substitution is to take u equal kx, in which case du is k dx, so you can replace dx by 1 over k du, and that's where the 1 over k comes from in each one of these three formulas. Another example that is treated easily by substitution, but that we will take as well as a standard formula, is the integral of 1 over a squared plus x squared. We've made this calculation when we introduced the arctangent function. What you do is factor out a squared at the bottom in order to get 1 plus a square, and then use the substitution u equal x over a. At the end, what we obtain is that the antiderivative of 1 over a squared plus x squared is 1 over a arctangent of x over a. Now let's turn to some tricks that you may or may not be familiar with. One of them is completing the square. So let's look at an example. Let's say we want to integrate 1 over square root of 8x minus x squared. At first glance, it looks like there's not a lot we can do. Because of course we have the function 8x minus x squared that is plugged inside the square root, but we cannot do the substitution u is 8x minus x squared because the derivative 8 minus 2x is nowhere to be found. So the question is, what do we do then? You may remember that we have a standard formula for the integral of 1 over root of 1 minus x squared. And here we have a root of something minus x squared. So maybe we can try to manipulate this in order to match this formula. And one of the standard tricks in this case is to use to complete the square in this expression. What I mean by that is that we're going to rewrite 8x minus x squared as the opposite of x minus 4 squared minus 16. In other words, we get 16 minus x minus 4 squared. Now, if you don't remember how to complete the square, and if what I just wrote seems mysterious, let's go back and recap a little bit on completing the square. It all comes from this basic formula that if you take the square of a sum of x and a, then you get x squared plus 2ax plus a squared. And to complete the square, what we usually look at is rewriting this as x squared plus 2ax is a difference of squares, x plus a squared minus a squared. So yeah, I'm just rewriting the same formula differently. So now to complete the square, this is exactly what we do. We are going to, we have a quadratic function, and we want to replace the x squared term and the x term in terms of a difference of two squares. So the first thing we're going to do is make sure that we have coefficient 1 for x squared. So for instance, in this case, we had 8x minus x squared. I'm first going to write it with coefficient 1 for x. In other words, I factor out negative 1. And inside a parenthesis, I have x squared minus 8x. That I can compare with my formula x squared plus 2ax. This x squared minus 8x is the same as x squared plus 2ax if a is negative 4. Then I can plug a equal negative 4 in my formula. This x squared minus 8x, I can write it as x minus 4 squared minus the square of negative 4, which is the same as 4 squared. And that gives me, of course, this 16 minus x minus 4 squared that I had. And I can rewrite my integral in those terms. Okay, now it's one step closer to the formula at the very bottom. were giving us arcsine of x as an antiderivative of 1 over root of 1 minus x squared. We still don't have a root of 1 minus a square. We have a constant minus a square. That's not too much of a big deal. We can factor out 16 and then pull it out of the square root. When we pull 16 out of the square root, we're going to get a 4. And when I factored out 16 inside the square root, I got x minus 4 squared over 16, which I can write x minus 4 over 4, all of that squared. So now I have something that really looks like my formula at the bottom. I have square root of 1 minus a square, but I want this to be the square of the variable, so that suggests the change of variable u equal x minus 4 over 4, in which case du is just dx over 4. So we are lucky because dx over 4 is something that we have inside this integral. Specifically, I'm going to replace dx over 4 by du and x minus 4 over 4 by u. And so formally we obtain the integral of du over square root of 1 minus u squared. So now that matches our formula at the bottom, and what we obtain is simply arcsine of u up to a constant. And u was x minus 4 over 4, so that gives us our antiderivative. Let's do another one, just to make sure that we got this. This time it's a definite integral from 2 to 4 of the function 2 over x squared minus 6x plus 10. Again, it's not clear what to do here to find an antiderivative of this function, but we can try to simplify that, completing the square. So if I complete the square in x squared minus 6x, then I get x minus 3 squared minus the square of 3, in other words, minus 9. And to that, I add 10. Because it's x squared minus 6x is replaced by this difference of squares. So that gives me x minus 3 squared plus 1. That's good, because now my integral is the integral of something of the form a constant over 1 plus a square. That should remind us of this formula, giving us the integral of 1 over 1 plus x squared as arctangent of x. So that suggests to make the change of variable u is x minus 3, so that we have at the bottom 1 plus the square of the variable. Of course, if we do that, du and dx are the same thing. So we obtain the integral of, pulling out the 2 that is at the top, we obtain integral of du over 1 plus u squared. And we have to change the bounds of integration because we're using a substitution for a definite integral. So when x is 2, u is 2 minus 3, in other words, negative 1. And when x is 4, u is 4 minus 3, so 1. An antiderivative of 1 over 1 plus u squared is arctangent u, and we have to evaluate that between negative 1 and 1. So we get 2 times arctangent 1, which is pi over 4, minus arctangent of negative 1, which is negative pi over 4. So we get 2 times pi over 4 plus pi over 4, which is pi over 2. In other words, we get pi. Now turn to the next video to see a few more tricks.